Meet the crew of Artemis III, weighing a dormant black hole. Evidence for a long-gone early planet. How robot probes could take over the galaxy. And in Space Bites Plus, scanning 3i Atlas for alien signals. All this and more in this week's Space Bites. Well, we recently saw the launch and successful return of the Artemis II mission, which sent a crew of astronauts around the moon. And last week, NASA introduced us to the astronauts who are going to be part of the Artemis III mission. So we've got NASA astronauts, Randy Bresnik, Andre Douglas, and Frank Rubio, and then ESA astronaut, Luca Parmitano. And so NASA rolled out this crew of astronauts and then also talked about what the plans are for the Artemis III mission. And the current idea is that there's going to be 3 launches in 2027. So first up, you're going to get the launch of the Blue Moon lander from Blue Origin. That's going to go into orbit. And then you're going to get a launch of the astronauts on board a space launch system in an Orion capsule. They're going to meet up with the Blue Moon capsule, and then they're going to demonstrate that they can dock, that they can transfer into the capsule. Then they're going to go back into the Orion capsule. And then around the same time, a SpaceX Starship that has been modified for this purpose will also launch. And then they're going to dock the Orion capsule to the Starship. Now, the Starship won't have any of the life support systems built in inside, so they're not actually going to try to go inside the lander, but hopefully they will demonstrate that they can dock with both of these spacecraft. And this is really clever, I think, because it's going to give both of these companies that are absolutely in a race with each other, SpaceX and Blue Origin, a chance to compete, a chance to prove if they can get their hardware together in time. SpaceX Starship, obviously they're having the various issues with getting this to a point where it's fully reusable. Blue Origin, they just had a rocket explode. And so the pressure is really on both of them to try and get this together by 2027, which is just a year away. So if all goes well, we will see all of these docking tests. And this, as in the words of NASA Administrator Jarek Isaacman, this is to buy down the risk, that there are a bunch of risky issues that they're still thinking about in terms of the landers. This will allow them to test all of that technology out and be ready for the 2028 human landing on the moon. And speaking of the human landing on the moon, we got an update from Axiom Space. They're the company that's working on the spacesuits that will be used in the lunar environment. The technical term for the Axiom suit is the Axiom Extravehicular Mobility Suit, or AxiMU. You can see what the suit looks like, but we now see what the inner layer is going to look like. And this was developed by Prada in partnership with Axiom Space. And this is called the Liquid Cooling and Ventilation Garment. And of course, when you're in space, you are either in direct sunlight or you're in the shadow, and you have vast temperature differences on the lunar surface. And so the astronauts will need to be able to either keep themselves very warm or keep themselves very cool while they're in the lunar environment. And so this will pump water of different temperatures around the astronauts to keep them at their preferred temperature. The partnership Prada is an interesting choice. And in fact, my wife was like, why Prada? And according to Axiom Space, this is a good partner because they've got experience with garment materials and production. They have a very large stack in their process. And so they have experience working with soft materials and things like titanium, and are able to go pretty far down the supply chain to be able to source their various materials, and so have a high level of quality. And I think, obviously for Prada, this looks good. We built the parts of the spacesuits that are on the moon right now. Maybe that will sell more handbags. I don't know. And so you can see all of the pieces desperately trying to come together for the 2028 human landing on the moon from NASA. How do you measure the mass of an object in space? It's actually pretty tricky, but there is a hack. And that is that if there's anything orbiting around that object, now you can calculate the mass of it directly. And this was mathematics that was developed by Newton hundreds of years ago. And it works on moons, planets, and it works on supermassive black holes. And so astronomers have found a supermassive black hole seen early on in the universe when the universe was about 3 billion years old. But this supermassive black hole is quiescent. It is not putting out very much radiation. And so without that radiation, it's actually really tricky to be able to measure what the expected mass of the black hole is. But astronomers used another trick, which was that there was a natural gravitational lens, a galaxy cluster in between us and this more distant galaxy that acted like a natural magnifying glass. Then they used James Webb to examine the galaxy using the gravitational lens, and they were able to identify stars that were in orbit around the supermassive black hole at the heart of this galaxy. And from that, they were able to then measure directly the mass of the supermassive black hole. And they pinned it down to 6 billion times the mass of the sun, which is a very massive black hole, especially that it's being seen at around 3 billion years after the Big Bang. We got a story about this from Carolyn Collins-Peterson. And so speaking of supermassive black holes, one of the big ongoing questions is how these black holes were able to feed on material and pack on the mass so quickly. How do you go from nothing to 6 billion times the mass of the sun just within the first couple of billion years of the history of the universe? And it's, thought that you have this combination of the black holes start off pretty massive, they find other black holes to merge together, and you get this kind of doubling as they find larger and larger, more massive black holes. All along this time, they are also feeding on material. They're feeding on gas and material that is streaming in to the center of this galaxy. But it's been really hard to actually connect the dots, to try and find a way that a black hole would naturally be able to feed on this much material. It turns out that there are filaments that feed material through gravity down into the centers of galaxies and actually feed the black hole. And so now we've got some really cool images of this process in the Centaurus cluster. It's about 170 million light years away, so relatively close, astronomically speaking. We've got images from Hubble that sort of showed the larger environment and showed how you've got these filaments around the supermassive black hole. And then we've got more information from Webb that actually shows in detail how this region is funneling material into the supermassive black hole, kind of force feeding the supermassive black hole. And so by measuring the rate of material that's going into the black hole, and then this gives us a better sense of how supermassive black holes got so big so early on in the universe. Got a story about this from Evan Goff. And speaking of supermassive black holes, of course, there is a supermassive black hole at the heart of the Milky Way, and this is Sgr A star. It has merely 4.1 million times the mass of the sun. And one of the features that we almost always see with supermassive black holes is winds. And you may wonder, how can you have wind coming from a black hole? Aren't they supposed to suck material in? Well, they do absorb material, but they can only absorb so much, and they get this accretion disk that forms around the black hole. The black hole is rotating. Magnetic fields around the black hole are interacting with this accretion disk, and that causes winds to blow out from these black holes. But it's never been seen around Sgr A star until now. So astronomers mapped out the gas around Sgr A star, and they found a large cone-shaped structure, essentially of emptiness, in the region around the supermassive black hole. And this matches the kind of structure that you would expect to see, a cone, a wind coming out of one of the poles of the black hole that is clearing out this material. We've got evidence of the winds coming from this supermassive black hole. And the wind isn't very powerful, astronomically speaking, and it's thought that it probably wanders over time. I've got a story about this from Evan Goff. Every week, we do a vote on our channel where you tell us what you thought was the most important space story of the week. And the winner last week was a galaxy that doesn't spin. So thank you, everybody who voted last week. As I always say, we put this poll, these votes, into the post tab on our YouTube channel. So go there, find the polls, vote, and then the YouTube algorithm will start to spit these at you whenever we update them. And the new poll is ready for this episode that you're watching right now. And if you want to see this kind of thing more often, just make sure you like this video, subscribe to the channel, click on the notifications bell, and then just obey the algorithm. The solar system has 8 planets today, or 9 if you want to include Pluto, or well over 100 if you want to include any object that has hydrostatic equilibrium. I am not going to judge how many planets you think the solar system should have. But what we know is that in the past, it had many, many more. Early on in the formation of the solar system, there were dozens of large objects in the solar system. These would have crashed into each other, merged, got obliterated. This is the source of many of the families of asteroids that we see today. It was one of those collisions that probably created the moon. Other stuff was thrown into the sun. Other stuff was thrown out into deep space, never to return. But we know this happened, and we can actually see this happening in other protoplanetary systems. But finding evidence of the objects that were once part of these planets is really tricky. But now astronomers think they've identified that a meteorite was once part of an object that could have been about the size of Mars. So the meteorite is called NWA 12774. It was found in the Sahara Desert in 2019. And it's classified as an angrite, an extremely rare type of meteorite. Of the 80,000 meteorites that astronomers have found, only 68 are classified as these angrites. And they have a bunch of distinguishing features, but one of them is that they're silica poor. They don't have a lot of the silica minerals in the way that Earth and even Mars does. But when examining this meteorite, astronomers found a bunch of clues that it was once part of a much larger world. One is that they found chemicals that only really form once you have something that is under really high pressure, the kind of pressure that you only get from a planet-sized object. And then they found that the shapes of the crystals embedded in this meteorite also indicated that it had to be part of a much larger world. And so from all of these different lines of evidence, they were able to estimate that the original object that this meteorite was part of had a radius of at least 1,800 kilometers, which sort of puts it at the moon class, or even as large as 3,300 kilometers radius, which puts it in sort of Mars class. And so this could have been part of a world that was the size of Mars orbiting the solar system, and now it's gone. And we've got more information about this from Andy Thomaswick. All right, I'm going to show you a picture now, and this is a real image of a protoplanetary disk, which is a newly forming planetary system. And we're now in this era where astronomers are regularly able to take images of these protoplanetary disks. The first one that was ever seen was in 1984, around the star Beta Pictoris, but now we have hundreds of examples of protoplanetary disk images. And just by looking at it, you know this thing is swirling, right? It looks like a galaxy, or it looks like the drain in your bathtub. This thing is turning. But measuring the rotation rate of the protoplanetary disk has actually been very challenging, because you just don't have the sensitivity to measure the rotation rate. But now, thanks to the Sphere instrument on the European Southern Observatory's Very Large Telescope, astronomers were able to actually measure the rotation rate of this protoplanetary disk. And it's not the same rotation across the entire disk. You've actually got little regions where the rotation is off what you would expect. And the astronomers expect that this is because there are giant planets embedded in the disk that are pulling at material differently than the rest of the disk. And again, it just boggles my mind that we can look directly at newly forming stars and the planetary systems around them. And you can identify gaps in the rings where new planets are probably forming. I've got a story about this from Carolyn Collins Peterson. People always ask me when we're going to have the James Webb version of the Hubble Deep Field. And the answer is it's going to probably be a few years. That, James Webb is very, very busy right now. Astronomers have a lot of specific targets. They don't have the time to go and just observe one spot in the universe for a very long period of time. But different teams are working on their versions of this, sort of building up. And eventually in a couple of years, they will have this conversation, agree on whatever the deep field version of James Webb is going to be. And we got an incredible release from one of these teams that is working on surveys of the cosmos with James Webb. And this is the Cosmos Web Group. And this is the Cosmic Web Project. And the Cosmic Web has been looking at a region of the sky that is bigger than the full moon, and yet has done 255 hours of observation across this region. So that gets you a lot of distance. And the goal with Cosmos Web is to try and see the large-scale structure of the universe early on in the history of the cosmos, where you've got these filaments containing millions of galaxies in these long threads, and then these surround the cosmic voids. You've probably heard about the Buddhist void. These filaments are around those gigantic voids, and that this structure started out early on in the universe and has then evolved into the structure that we see today. And so you've got the most detailed map of this large-scale structure, this cosmic web of the universe ever taken. And just so incredible compared to what was tried with the Hubble Space Telescope. And it gives you this insight. You can see the Hubble version of this same kind of survey and now the James Webb version of this. And this is, hopefully, this will whet your appetite for as we get towards a James Webb deep field. Got a story about this from Matt Williams. In the 1970s and 80s, two physicists published a series of papers that looked at the likelihood of extraterrestrial intelligence. And the theory is known as the Hart-Tipler conjecture. And if you've watched my channel, I am often bringing up a version of the Hart-Tipler conjecture. And the gist is that advanced civilizations will probably develop the technology to build self-replicating robot probes, von Neumann probes. And then they will send these probes to various star systems. They'll produce more copies of themselves, and they'll go on to other star systems and eventually consume the entire galaxy that they're in. But beyond just staying within the galaxy, they can probably jump to other galaxies. When you know that the universe is big and old and that there are planets that probably were capable of forming life billions of years ago, then you would expect that other civilizations, if they're out there, would have had a head start on us and would have sent out these self-replicating robot probes, these Borg, to go on to consume giant regions of space, grabby aliens. Now, David Kipping, who runs a Cool Worlds lab and is a YouTuber as well, just published a new paper talking about the Hart-Tipler conjecture and really just kind of calculating how rare would life have to be for us to see the kind of universe that we see today without the alien probes crawling everywhere. And he's done the math and has a bunch of different versions. It all depends on how fast can spacecraft move from star system to star system. But he calculates that for us to see the universe that we see without the alien probes, that you would need between like 1 in billions and 1 in quadrillions of star systems to be the only place where life developed. And so this is leading to this idea that we are rare or even alone in the universe. Otherwise, we would see a ton of alien probes. Now, in addition to the paper, Kipping has also done a video on this subject and explained it and provided some simulations as well. So I'm going to put a link in the show notes. You should go and check out David's video about this because, of course, he did the math and he's very eloquent about explaining the conclusions. And so if you've watched my channel and you sort of heard my justification for why I think we're alone in the universe, I was referring to the Hart-Tipler conjecture. Kipping has done the math to sort of really put it in your face and make you lean on a bunch of assumptions. So I think it's an amazing paper, great video, and a truly haunting thought experiment about the universe. So check that out. I hope you're enjoying this week's episode of Space Bites. Now, if you're watching this on YouTube, you had to watch an ad at the beginning. We can't turn this off, but we think that you should watch our videos without ads. And of course, we're able to do that by hosting our videos over on Patreon completely for free. And so if you want to watch the same video, get no ads, and you don't have to pay us, you don't have to become a member, you don't have to do any of the Patreon stuff, you can just watch it right now. I'll put a link down in the show notes. And this week's bonus story is that SETI researchers did a technosignature search on interstellar object 3I Atlas. What did they find? Well, you have to watch that segment. And of course, these are just a fraction of all of the stories that we're covering on Universe Today. I always talk about this. We are covering 30 to 40 plus space stories on Universe Today, original reporting that you're not going to see anywhere else on the internet. I don't have time to go through all of those stories here in Space Bites. But if you don't want to watch the website every day, every hour, you can sign up for my free weekly email newsletter. I do a write-up of every single story that we covered on Universe Today this week. All my own writing. It's completely free. There's no ads. Check it out. Go to universetoday.com/newsletter to sign up. Now, you probably heard me say the name Matt Williams in this episode several times, and you've heard me say it in other episodes several times. And now I'm going to encourage you to check out Matt Williams' podcast. I've got a bunch of information, but first, I'd like to thank our patrons. Thanks to Abe Kingston, Andrea Pedretti, Brian Bodie, Caradon, Chuck Hawkins, Commander Baylock, Dark Finga, David Gilton, and David Matz, Enthrallo Reading and Math for Toddlers, Eric Lindstrom, Evan.Pro, James Clark, Jeremy Mattern, Jim Burke, Jordan Young, Marcel Smits, Michael Purcell, Nordspace, OneStepForAnimals.org. Please follow my nephew at VBrick6994, Renkivey, Richard Williams, Sean Sargent, Stephen Fallon-Munley, Team 49, Telescopes Canada, Vlad Chiplin, Wolfgang Klotz, and Zeldabord Galactic Defender, who support us at the Master of the Universe level, and all our patrons. All your support means the universe to us. So I say the name Matt Williams often several times a week, and Matt is one of the writers at Universe Today. But that is like just one of the things that Matt Williams does. He is a science fiction author with several published books. He is a freelance writer that has worked on a bunch of other websites in addition to Universe Today. And he does his own podcast. Now, Matt's podcast is called Stories from Space, and he's got 3 seasons under his belt so far. He's got about 24 episodes per season. And these are a mix of his own reporting and interviews with some pretty incredible names. Like recently, he just talked to Slava Turishev, who's one of my favorite people to interview, you know, the mind behind the solar gravitational lens, but works on a lot of other things as well. So I'm going to direct you to check out Matt Williams' podcast. Now, he is hosting it on Patreon as well, but again, you can just listen to the episodes there if you want to hear those interviews and hear Matt. So check out patreon.com/House of Williams. But I'll put links to the show notes so you can get it from Apple Podcasts and other locations. All right, those are all the stories that we had this episode. We'll see you next week.